Hey everybody, welcome to AlgoExpert. In this video, we're going to be covering the depth-first search algorithm. This is a very famous graph traversal algorithm. It is the sibling of breadth-first search, if you may, and it's a pretty easy algorithm, mainly because you can write it or implement it in 2 or 3 lines of code. But that being said, it is, by all accounts and measures, very important to know. It's a must-know for if you walk into any programming interview room. And so without further ado, let's dive into it. We're going to be traversing or exploring a graph. And in our example, the graph is going to be a sort of tree-like data structure that is going to have a bunch of nodes. And each node is going to have a name in the form of an alphabetical letter, a letter in the alphabet, like A, C, K, J. And each node is also optionally going to have some children nodes. Like A here is going to have B, C, and D as its children nodes. B is going to have E and F, etc. But C is not going to have any children nodes. And so we are asked to traverse this graph in a depth-first search way. And to, as we traverse it, to grab the names of all the nodes, put them in an array, and return that array. So in the top right corner here, you can see the solution. This is going to be the array that we're going to want to return. A, B, E, F, I, J, C, D, G, K, H. So how does depth first search work, right? Well, as its name suggests, we're going to be going deep rather than wide. In other words, we're going to explore a specific branch, probably the first branch in our graph, all the way down as deep as we can before exploring the next branch. And that next branch, we're going to explore it all the way down, as deep as we can before exploring the next branch. This is opposed to breadth first search, where we kind of explore level by level. So here we're going to go, in this leftmost branch first. Then we're going to go in this sort of inner leftmost branch, then this inner rightmost branch, and so on and so forth. And so this algorithm can actually be implemented pretty beautifully in a sort of recursive way, where we call the depth-first search function on each child node one after the other. It's not really recursive, but basically the way it works is, and I'll repeat this a couple of times, but whenever we are at a given node, we're going to add that node's name to the final array. And then for every child in its children nodes, we're going to call the depth-first search function and probably pass in the final array. So let me repeat that. For every node, we're going to add that node's name to the final array. And then for every child node that node has, we're going to call the depth-first search function and probably pass in the final array. So let's actually look at an example of this with the example that we have in front of us, and we'll rebuild our final array here at the bottom. So we start at the node A, the root node, and we call the depth-first search function on it. So the first thing we do is we pass in the letter A to the final array. We add it to the final array. And then for every child node of A, meaning B, C, and D, we call the depth-first search function. So we start with the first child node, B, and we call the depth-first search function. So now we are at B. So the first thing we do here, grab B's name and add it to the final array. And then for every child node in B, which are E and F, call the depth-first search function and probably pass in the final array. But we start with the first child node, which is E. So now we are here. So grab E's name and add it to the final array. And then for every child node of E, call the depth-first search function. Now you'll notice E is at the end of a branch. It doesn't have any child nodes. So we're done. We can kind of escape from E. And so we've explored an entire branch as far deep as we could. So now we call depth first search on the second child node of B, which is F. So we are here now. We can add f to the final array, and then we can call depth first search on both of f's child nodes, I and j. Start with I, add I to the final array, then call depth first search on the child nodes of I, but we don't have any because we're at the end of a branch. We've explored this entire branch. So now call depth first search on j. We're here now. Can add j to the final array, call depth first search on any child nodes that j might have, but it doesn't have any. So we're done with this branch. We can climb all the way back up to C. So now we call depth first search on the second child node of A. We've explored this entire left part of the graph, and now we call depth first search on C. So we can add C to the array. C doesn't have any child nodes, so we move on to D. So add D to the array. Let's erase the circle now. Let's rewrite D. So now we call depth first search on the child nodes of D, which are J or G and H. Start with G, add G to the array. Let's remove the circle, add G to the array. Then we call depth first search on the child node of G, which is K. So add K to the array. And then finally, we're going to climb back up and get to this H and add H to the array, and we're done. So you'll notice that if we grab this array and compare it to our starting array, or our solution array at the beginning, they are identical. A, B, E, F, I, J, C, D, G, K, H. And so we have our solution. That's how depth first search works. So now, if we dive into the space-time complexity analysis, this is a bit involved compared to a lot of other algorithms, mainly because we're going to be dealing with two variables. We're going to be dealing with vertices and edges. So in a graph, a vertex is kind of like a node in the graph. So here in this case, A, B, C, all the nodes that we have in the graph are literally vertices of the graph. And then all the edges in the graph, meaning the connected lines in the graph, are going to be represented by the E variable, short for edges. So this line between A and B is an edge. This line between B and E is another edge. And so the time complexity of this algorithm is going to be O of V plus E, where V is the number of vertices or nodes in the graph, and E is the number of edges connecting those nodes. So why is it O of V plus E? Well, let's think about what we were doing in the algorithm. We know that at one point or another, we traverse every node because we add every node's name to the final array, right? So that's the O of V. We traverse every vertex and add its name to the array. But on top of that, at every vertex, we iterate through the children nodes of that node, of that vertex, and we call the depth first search function. And when we iterate through those children nodes, we're probably going to be using a for loop. What's the length of that for loop? Well, it's however many children nodes we have. Or in other words, how many edges are coming out of the current node. So you'll notice here when we were at A, we had 3 children nodes because we had 3 edges coming out of A. When we're at B, we have 2 children nodes because we have 2 edges coming out of B. However, when we're at C, for instance, there are no children nodes, so we don't call the depth first search function on other nodes, and there are no edges here, and that kind of reflects this. And so that's why the time complexity is going to be O of V plus E. And then the space complexity is going to be O of V. So the reason it's O of V is twofold. First of all, for our particular question, we're storing an array that holds the names of V different nodes. So that's why it's O of V. But putting aside the array that we store, in the worst case scenario, we would have the actual depth first search function or algorithm would take an additional O of V space. The reason being is we are adding, the way we did it by calling the depth first search function on all the child nodes, we are adding a bunch of frames to the call stack, right? And so you can imagine that as we go deeper and deeper and deeper in a branch, we keep adding frames to the call stack, because like when we call the depth first search function on A, before we resolve that function, we call depth first search on B, C, and D. But we start with B. And before we resolve depth first search on B, we call depth first search on F, on E and F. But before F gets resolved, we call depth first search on I. And then I gets resolved because it doesn't have any children nodes, and we kind of go back up. But so in this example that we have, there comes a point where we have 4 frames on the call stack, right? We have A, depth first search on A, on B, on F, and on I. And so you can imagine an example where imagine we had a graph that only had one huge branch. So it would go from A to B to C to D to E, etc. In that case, we would keep calling depth first search on all of these nodes, and depth first search of A wouldn't resolve until we've resolved all the other ones. And so we would reach a point where we'd have V frames on the call stack. So that's why we can have a worst case space complexity of O of V without even counting the array that we're storing. If you count the array that we're storing, then it's also O of V. In any case, right? But so that's it for the space-time complexity analysis. Make sure that you understand this aspect of it. And let's dive into the code walkthrough. It's just going to be a few lines of code. All right, so we've got our node class defined. It's a very simple class. Every node has a name, has an array of children nodes initialized to an empty array. You can then add a child to the node by just appending a new node to the children array. So then we've got our depth first search function defined, and it takes in this array that we're going to return at the end with all the names of the nodes. So the first thing we're going to want to do in this depth first search function is exactly what we mentioned in the conceptual overview, which is to append to our array the node's name. So self.name, right? Because we're calling the depth first search function on the node. So we can refer to it as self, or in JavaScript, this, and we append the name to the array. Then we say for child in self.children, child.depth first search, passing in the array. So for every child in the children, we call the depth first search function on the child, and we pass in the final array. And then lastly, we return the array, and we're literally done. So 4 lines of code to implement this algorithm. Again, why does this make sense? Well, let's say we have our example that we had in the conceptual overview with the root node as A. We append the name A, and then we start iterating through the children. We're going to start at B, and we call the depth first search function. And now we go back up into depth first search on B, and we append B, and we go through all the children and so on and so forth until we're going to get back all the way to the second child node of the root node, which was C, and so on and so forth. And this line here, returning the array, is only going to be useful for the very first call of depth first search. Because for every other call here, we don't care about the return value, so it just kind of gets thrown or absorbed in the nether. Anyway, so this is going to run in O of V plus E time, where V represents the number of vertices or nodes in the graph, and E represents the number of edges in the graph. And the space complexity is going to be O of V. This is because of the array that we return, that is going to have length V, and also in the worst case, where we'd have a graph that has one gigantic branch, we would have V frames on the call stack used up at once with this approach. So that's it for this video. I hope it was helpful. I hope it was informative. Make sure to understand depth first search. It's an awesome algorithm, and you definitely want to be able to nail it in an interview. And I'll see you in the next video.